I should be recording this. So to catch people up watching the recording, I started recording, crap. To catch people up watching the recording, we're trying to prove this claim. We have this sequence, f of 0 equals 5, f of 1 equals 16. This might be good for everyone else too to get a recap. And the sequence is defined recursively to say that f of k equals 7 times the previous minus 10 times the second previous for every integer k greater than or equal to 2. The claim is that we can actually rewrite this sequence in a more explicit way, saying that for all n greater than or equal to 0, f of n is actually going to equal 3 times 2 to the n plus 2 times 5 to the n. And actually, this is kind of a nice claim because explicit formulas are way better than recursive formula usually. Right? I like them a lot better because with this explicit formula, if you ask me to calculate f of 100, I just plug it in a calculator and calculate it. If you ask me to calculate f of 100 using the recursive way, well, hold on. First I have to calculate f of 2, then f of 3, then f of 4, then f of 5, then f of 6. I have to do that 100 times to get to f of 100. So explicit's way better if we can manage it. And so the claim, is it true? So far what we've done is we've done our base cases, and we've done n equals 0 and n equals 1. And the reason we had two base cases is because we noticed here our recursive formula, which we're going to use, uses two previous terms. And so we needed two base cases to kind of match that. If we didn't have two base cases, we tried to start at n equals 0 here. So we had just one base case, just the n equals 0. So we start at n equals 0 here to try to prove everything up to n is true, then n plus 1. Well, that means if we only have n equals 0 as our base case, the first thing we're proving with our inductive step is n equals 1. That's the first thing that we show works by this recursive nature thing here. But the problem with trying to prove n equals 1 with the inductive step is, well, we said we need the two previous. But 2 previous from 1 is negative 1. And there is no f of negative 1 here. So it makes no sense. So since we need the 2 previous terms to prove the next one, right, the first thing we can prove with our inductive step is f of 2, because that's the first thing we actually have 2 previous terms. And so to reflect that, we want to have n equals 0 and n equals 1 as our base cases. So then trying to prove n plus 1, then starting at n greater equals 0, we'll prove n equals 2. We'll prove n plus 1, which is 2. We'll prove 2 as the first thing in our inductive step. To start with base cases 0 and 1, the first thing in inductive step is 2. That makes sense. So we did the standard induction thing here. We said let n be any arbitrary integer so that n is equal to 1. Assume it works for everything between 0 and n. So everything between 0 and n, any k there, assume that we can write our sequence in this explicit way, f of k equals 2 times 2 to the k plus 2 plus 5 to the k. And now we want to show that if we assume it works for everything up to n, it'll work for n plus 1. But, so we're trying to work with this n plus 1. The question is, we really want to write it in this recursive way. But how do we know that f of n plus 1 we can write like this? It only works if our index is greater than or equal to 2. How do we know n plus 1 will be greater than or equal to 2? Alfred, Jai, or Jenny, you have the floor.
Put n plus 1 in the range we wrote on the top and see if it's true for that.
Yeah, I mean, but what factor are we gonna need? How would we know anything about n plus 1 and if it's greater than 2? The key is we know n's bigger than or equal to 1. And so if n's bigger than or equal to 1, well, actually, first I'll just say consider f of n plus 1. Consider f of n plus 1. That's kind of what we're doing. But as part of that, note, since n is greater than or equal to 1, n plus 1 is bigger than or equal to 2, right? Oh, yeah. Right, that's kind of the whole point of assuming this range. The whole point of assuming this range of n greater than or equal to 1 is number 1, so we have these two previous base cases, so that works out. But it's also important that then that ensures that n plus 1 will be greater than or equal to 2, so we can use a recursive formula. It's actually kind of the same thing. If we had n greater than or equal to 0 here, like we had before, n plus 1 would be greater than or equal to 1, so we couldn't use this recursive formula. That's kind of exactly what I'm saying. In order to be able to use the recursive formula and have two previous terms, we need n greater than or equal to 1. That ensures n plus 1 is greater than or equal to 2, the thing we're trying to prove it about. P of n plus 1. We're trying to prove f of n plus 1 works the way I think it does. So n plus 1 is going to equal to 2. I'm talking fast. Thus, by the definition of our recursive sequence, because n plus 1 is greater than equal to 2, f of n plus 1, right, for everything greater than equal to 2, will equal 7 times the previous, which is just f of n, minus 10 times the 2 previous. All right. And now here's where I'm going to go quickly, because this part doesn't quite matter to you all. And that, well, actually, first, this part does matter. So now this next part is, remember, in our side, we want to show that, well, we really want to show that we can write f of n and f of n minus 1. We can write both of those in this explicit formula form. Really want to show that, because then we can do some algebra and all work out. So, but why? Why can we write f of n in this form? And why can we write f of n minus 1 in this form? How do we know we can? And this is where our inductive assumption comes in, because the inductive assumption says if it works up to n, we assume it works up to n, that's the inductive assumption. Well, I'll prove it works for n plus 1. But how do we know both of these are kind of in our inductive assumption? Well, our inductive assumption was this. We said assume for all integers k, just that k is between 0 and n, it'll work. So we just need to show that n and n minus 1 are between 0 and n, because then by our inductive assumption, it'll work. If this is just things less than n plus 1, so we're assuming they work, and we'll show it goes to the next one and the next one, that kind of thing. So we just have to verify. So we need to verify n and n minus 1 are between 0 and n, because of that, to make sure by inductive step f of n and f of n minus 1 work. So that's what we're doing now. So what I'll say is note that since we have n's greater than or equal to 1, 0 is certainly greater than or equal to 1. Or since 1's greater than or equal to n, or sorry, since n's greater than or equal to 1, we'll certainly have that n is greater than 0 and greater than or equal to n. I think that makes sense. Further, since 1 that's equal to n, we have that 1 minus 1 is less than or equal to n minus 1. Right? And 1 minus 1 is just 0. Thus, 0 is less than or equal to n minus 1, less than or equal to n. Clearly, n minus 1 is less than or equal to n. So n is in this range, and n minus 1 is in this range right here, the one we care about. And we're assuming by the inductive step it works with the n. So if you're in this range, then we can, in fact, write f of k in the explicit way. So we can write n and n minus 1 in the explicit way by our assumption, is all we're saying here. Hence, by our assumption, f of n minus 1 is going to equal 3 times 2 to the n minus 1 plus 2 times 5 to the n minus 1. And f of n is going to equal 3 times 2 to the n plus 2 times 5 to the n. Just because these are the two, this is the proposed explicit formula, so then we can write everything like that. So we're going to assume we can write the two previous like that by our inductive assumption, and then prove we can write the next one like that. So then here's where the kind of unimportant part is, just because this is for the specific. Everything we've done here is pretty general, right? Like a lot of this applies to every sequence. This next part just applies to this particular sequence. So I'm going to go really fast, just because it only applies here. So then here's where we put everything together. Where we then show, okay, f of n plus 1, which we can write like this. We know we can write f of n and f of n minus 1 in this explicit formula way. Let's show that if we actually plug these explicit formulas in here, we can get f of n plus 1 also in that explicit formula kind of way. So then f of n plus 1, which equals 7 times f of n minus 10 times f of n minus 1. This is going to equal 7 times, I'll plug this in here, 3 times 2 to the n plus 2 times 5 to the n minus 10 times f of n minus 1 is 3 times 2 to the n minus 1 plus 2 times 5 to the n minus 1. Now we did this in the aside already, so I'm just going to quickly for this, but you can pause and actually see all the steps I'm going to do are going to work. This is going to be the same thing as 7 times 3 times 2 to the n plus 7 times 2 times 5 to the n minus, I'm going to put a 2 out. I'm going to take a 2 out of the 10 and multiply it here. It's going to be 5 times 3 times 2 to the n, because of 2 times 2 to the n minus 1 is 2 to the n. And then when I multiply by this in the distribution, I'm going to take the 5 out instead and multiply it by here. This is going to be minus 2 times 2 times 5 to the n. You have 2 2's because once you take the 5 out of here, you have a 2 left over. So we have 2 times this 2 times 5 to 5 to the n minus 1, so 5 goes up there. I think you'll see this all works. Now I'm going to subtract, I'm going to factor. We have 3 times 2 here, 3 times 2 to the n here. And with 2 times 5 to the n here, 2 times 5 to the n here. This is going to be 7 minus 5 times 3 times 2 to the n plus 7 minus 2 times 2 times 5 to the n. Right? Factor that out, you get 7 minus 2. Factor that out, you get 7 minus 5. For 7 minus 5, that's just 2. So this is 2 times 3 times 2 to the n. 7 minus 2, that is 5 times 2 times 5 to the n. And that all just works out. 2 times 2 to the n is 3 times 2 to the n plus 1 plus 2 times 5 to the n plus 1. Which is exactly what we wanted. We wanted to show that we could write f of n plus 1 in this way. We just showed that, okay, if it works for the 2 previous, it will in fact work for f of n plus 1. So, therefore, conclusion. Therefore, for all n greater than or equal to 0, f of n does in fact equal 3 times 2 to the n plus 2 times 5 to the n. Because if it works for the 2 previous, it'll work for the next one. And by our base case, it works for f of 0 and f of 1, the OG 2 previous. So it works f of 0, f of 1. By our inductive step, it'll work for f of 2. And by our inductive steps, as it works for f of 1, f of 2, it'll work for f of 3. So it works for f2, f3. By our inductive step, it works for f4. It works 5, 6, 7, 8. It works for everything. Conclusion, done. Questions? This is a very long example. This is a very, very long, strong induction example. And this is pretty far down the book. This is one of the hardest ones you'll ever see. So if you can understand this, you can really understand it. Now, what made this hard was the meat of this problem, like the meat I've been calling this part down here, was kind of difficult, not easy. But if you ignore this, I'll be honest with you guys. For the final exam and all your tests and homework and things like that, the actual meat of a problem is worth like 2 points. Where most of the points lie are in the form. And so the important things you need to hit in the form. You need your base cases right. You need to actually show all your base cases are true. You also need, right, to start your inductive step at the right spot. So this n greater than 0, n greater than equal to 1, this should overlap your last base case. These should overlap. Because what you're saying is you want to show if it works for n greater than equal to 1, everything up to that, it'll work for n plus 1. Right, so the first thing you're proving with your inductive step is n plus 1 for the smallest n. 1 plus 1 is 2. So the point being, you want these two to overlap. And then you need to assume your inductive step. So once you have this overlap with your base case, you want to assume your inductive assumption, being that for every integer between your first base case, 0, and n, if it works for that, or assume it works for that. Yeah. So you assume for all things between 0 and n, so between your first base case and n, the claim is actually true. This is the claim, right? This is the claim we're making. You can't see that. This is the claim we're making right here. So then assume the claim is true for everything up to n in this way. And then you want to show the claim is true for n plus 1. And so for sequence things like this, we have a couple things to do. Number one, once we consider f of n plus 1, we probably need to show that this index allows us to use our recursive formula if it's a recursive thing. Here we needed k greater than or equal to 2. So what I need to do is show that by our letting n be greater than 1, greater than or equal to 1, this will be the right index where you can use a recursive formula. We want n greater than or equal to 1, so we can show n plus 1 is greater than or equal to 2, so we can use our recursive formula. And by the way, if this didn't work, right? For example, if our recursive formula only worked for if our recursive formula here only worked for things greater than or equal to 3, for example, it's only worked for things greater than or equal to 3. What do? Well, what you do is just say, okay, I'm gonna need my n plus 1 to be greater than or equal to 3. Therefore, I need my n to be greater than or equal to 2. Therefore, I need another base case because this always has to overlap the base case. So if you need greater than or equal to 3 here, you would need a third base case. And then you start at 2, and you have 3, so it works out. So you just go through and make it work. And then after that, you need to show that the things like these things that show up in your recursive formula, that whatever you're trying to say about them is actually true. And so in order to say they're actually true, you need to verify that this index n and this index n minus 1 are actually between 0 and n, where you assume it works. That's our next step. And then you have the meat of it, and then you're done. So the form is important here. Any questions? Okay, well, because we spent so long on that, I mean, you guys can leave anytime you want. This is all optional. I'll also go over after we want to talk about some of the homework 12, right?
Yes.
Any ones in particular?
Number 2, I believe.
Number 2. Oh, I like number 2. Okay. So let's just do it. So number 2 on homework 12 went like this. So the claim was, for all sets A, B, and C, I think it was this, A union B intersects C equals.
Oh, sorry, I mistake that one. That should be number 1. I'm so sorry.
Number 1. Okay,
number 1 was confusing.
Yeah, 1 was confusing. For all sets A and B, we're trying to show that A not B cross A not B equaled A cross A not A cross B union B cross A. Now, from the start, I'll tell you that once you know how to work with sets, you can see this is true before you even do anything. So why is this true? Well, let's think about it. This A over B cross A over B, it's a direct product. And direct product is just the set of all ordered pairs where the first coordinate comes from here and the second one comes from here. So things in here look like XY, where X is in A over B and Y is in A over B, right? That's what direct product means. Now here's the idea. If X is an A, not B, and Y is an A, not B, what do we know? Well, number one, we know that X and Y are both an A. Because you're an A but not in B, that means in particular you're an A. And Y is an A but not in B, so Y is an A. So this means X and Y are both an A. X is an A, and Y is an A. So XY is in A cross A. Because A cross A is just a set of all things where the first coordinate comes from A and the Y coordinate comes from A. Which is exactly what we have here. So X and Y is in A cross A. But it can't be anything in A cross A, because in particular, X and Y both can't be B. They can't be in B. They can't be an element of B. Because they're an A, not B. A, not B. So if X and Y are in A cross A and they're not an element of B, let's think about this, right? The elements of A cross A, if you're in A cross A, then either, right, X is also in B. This is the weird part. Then either XY is going to be in B cross A, XY is going to be in A cross B, or neither, which is the case where X must not be in B and Y must not be in B. So here's what I'm saying here. If you have an ordered pair XY, right, where you know X and Y are both in A, maybe X is also in B. And if X is also in B, then you're in B cross A. Or maybe Y is also in B. And if Y is also in B, then you're in A cross B. Or neither. You have neither. Neither is the case where both X can't be in B and Y can't be in B. And if you're in that case, then you must be in the A cross A case, but get rid of both of these. Because we know we're actually in this case because X is not in B and Y is not in B. This is a very loose description of kind of what's going on here. The point is because X is not in B, right, because this is not B, and Y is not in B, we can't have XY and B cross A, and we can't have XY and A cross B. Because XY and B cross A, that implies X is in B. The first coordinate's in B, but X can't be in B. XY and A cross B, that implies that Y is in B. The second coordinate has to be in here, but Y is not in B. So therefore, XY has to be specifically in the A cross A, but you got to get rid of both B cross A and you got to get rid of A cross B. You got to get rid of both of them because XY can't be in either. That's the idea. I don't know if that made any sense or not. I hope it did. But if not, we have a rigorous proof to really show why it's true. So for all of these proofs, we have to do double set containment. That means you just show that this set contains this set, this set contains this set. So I'll do proof. I'll say need to show that A over B cross A over B is a subset of A cross A over A cross B, or not over, not including A cross B union B cross A. And we need to show that A over B cross A not B, that's what we're saying, A not B, contains, in the other way, A cross A, not A cross B, union B cross A. All right. So let's do the first direction like that first. And to prove any of these containment things, to prove containment, to prove like this set's a subset of this set, you just need to show that every element of this set is an element of this set. This is the element method. So to prove every element of this set's an element of this set, just take any old element of this set and show it must be an element of this set. So let X be any old, which is another way of saying any arbitrary / particular, I'm sorry. Let XY be any old arbitrary / particular element of A over B cross A over B. We know that elements here are going to be ordered pairs because this is a direct product. That's why X cross XY, not X. So here's where we just straight up use our definitions. Since XY is in A over B cross A not B cross A not B, by definition of direct product, what do we know about X? What do we know about Y?
Both are in A.
I think we're kind of skipping a step. They're both in A not B, right?
Yeah.
Yeah, this is the first step. Direct product literally means if you're in this direct product, that means the first coordinates in the first set, the second coordinates in the second set. And it goes both ways. If we know that X is in A not B and Y is in A not B, then we know that XY is in A not B cross A not B. It goes both ways like that. Direct product just has the coordinates match up like that. But now here's your next step. Since X is in A not B, how does X relate to A and how does X relate to B?
B complement?
Yeah, you can put it like that. So first of all, how does X relate to A? If you're in A not B, how does X relate to A? Is X in A, not in A, what?
X in A, but not B.
Yes, exactly. Here we get that X is in A, but X is not in B. And but's kind of the same thing as and in this case. X in A and X not in B. Similarly, Y in A not B means Y is in A and Y is not, big old not, in B. That's exactly what it means. So all of these proofs have a deconstruction phase and a reconstruction phase. So far we have deconstructed, right, what it means to be an A over B cross A over B. What it means to be an A over B cross A over B is that X better be an A, but not B, and Y better be an A and not B. That's what it means. We deconstructed this down to the elements, down to the individual sets, and what it means. Now let's reconstruct, or we're going to try to build it up to get back to here. But let's kind of work backwards. The reconstruction phase is kind of more creative. Deconstructive, it's just kind of like, oh, okay, just kind of keep using the definitions to get us down to the kind of the base things. This is as far as down as we can go. Reconstructing, there's multiple ways we can reconstruct this, right? We could reconstruct this back up to get to here. Like we could say, oh, because X is in A and X is not in B, X is going to be in A, not B. Because Y is in A, Y is not in B, Y is going to be in A, not B. And because X is in A, not B, and Y is in A, not B, that means X, Y is in A, not B, cross A, not B. That's what we started with, right? That's kind of useless. We want to kind of reconstruct it just so that it's also in something else. We want to rewrite it in a way that shows it's something else. So here's where we kind of want to look ahead and look at what we need. So note, to prove that XY is in A cross A, not A cross B union B cross A. To prove this, what would it be really nice to know? Like, what would the step before this have to say? So then we could conclude this. That's a good place to start. It's kind of like, what are we trying to get to here? It's like solving a maze, right? If you ever went to like a Red Robin when you're a kid or something like that, and you had like a maze crown thing where you try to solve this little maze. And then like, sometimes you can work from the beginning. A lot of times you go, okay, where am I trying to end up? You kind of work from the end and go, okay. You kind of do both. So that's kind of what we're doing here. we're kind of saying, where would I need to, like, where's my path have to go? So what would I need to prove before this to prove this is true? And if we can't think of anything, we're in deep trouble, right? If we can't think of anything, then how would we ever prove this true?
Can we break down the other part on the right hand side? The AX B union BX A.
Okay. So, oh, sorry. I see what you're saying now. This X is more like a times than an actual X. So it's called, let's say cross. This is A cross B, B cross A.
Because it's like two of the elements, like X in A and Y in B. So we could, because we can rewrite the whole thing differently.
Yeah, I like that a lot. I think you're getting a little ahead of yourself. You were talking here. But here's the thing. If we want to show that XY is in this set, but not this set, it would be really nice to know. It would be nice to know that XY is in A cross A and XY is not in A cross B union B cross A. Wait, you guys didn't see that. Sorry. Right? If we know that XY is in A cross A and XY is not in A cross B union B cross A, well, that's really solid. If we know this, then we can prove this. Because that's what it means to be in A cross A, not A cross B union B cross A. What it means to be in this set is exactly this. XY is in A cross A and XY is not in A cross B union B cross A. Does that make sense? Last day for the test to speak now if ever hold your peace. Makes sense. So it would be nice to know this to prove this. But for this step, like how would we show this? Like what would we have to show that X is not in the union of two sets? If you're not in the union of two sets, how does XY relate to both of them? So if you're not in the union of A cross B union B cross A, could you be in A cross B? Could you be in the first one?
Yeah.
Well, let's think about it, right? Let's say...
Isn't it union used in case of if we think it other ways, as in we might not have X in A into B, but we could have it B into A.
I think I see what you're saying. Let's look at this really simple example. Let's stop thinking about A cross B, B cross A, all that. Let's just have two sets C and D. If you're not in the union, that means you're here, right? So if you're not in the union, could you be in A? Or sorry, could you be in C?
No.
Yeah, could you be in D?
No.
No. If you're not in the union, you're not in either one of them. Because if you were in either one of them, then by definition, you'd be in the union. Because the union just says you're in one or the other. And here's how we can actually prove that right? The way you prove that is you say, oh, okay, like Z is an element. If Z is in C union D, what that literally means is that literally, why am I sideways? So if you have Z is in C union D, that literally means that Z is in C, or, which I'll write like this, or Z is in D. That's what it literally means. So the negation of this is Z is not in C union D, is the negation of Z and C or Z and D. Well, how do I negate this? How do you negate an or statement?
By the De Morgan's law, take the not.
Yeah, perfect, Afra. Take not the first one and not the second one. Because if you can't have this or this happen, the opposite of this or this happening is that they both can happen. But then not Z and C, that just means Z not in C, and not Z and D, that just means Z not in D. So if you're not in the union, you must not be in the first one set and not be in the second set. If you're not in the union, you're not in both. That's just like by definition of union. So you can see that either by kind of doing like a negation here of the union, or just like draw a Venn diagram and look at it. Right? Both ways work. Or if you can think about it abstractly, that would work too. But either way, the point is, if you're not in A cross B union B cross A, you can't be in the first one, and you can't be in the second one. Because if you were in either one of them, you'd be in the union, but you're not in the union. So you can't be in both of them. Does that make sense? So what we're saying here is to prove this, to show this, it would be nice to know this. So if you know the blue, you can show this. Oh, okay. And if you can show that XY is an A cross A, and you can show XY is not an A cross B, B cross A, well, you can show this, because that's just by definition. All right. Let's go one step down. To show this, to show XY is an A cross A, what do we need to show? This one's the easy part. Like, how can we verify an element is in A cross A? What's it mean? Maybe we'll do an example.
Isn't it like the power set of A's?
If one is 1, 2, and the natural numbers cross the natural numbers.
Yes.
How do you know?
Because both of them are like 1 is also a natural number and 2 is also a natural number.
Yeah, that's it. To show XY is an A cross A, just need X and A and Y and A.
Wouldn't it be like having pairs of elements in A, as in like power of A?
So the power of A would be the set of subsets of A. And we don't care that we don't even want X and Y to be subsets of A. We just want X and Y to be elements of A.
Okay.
It's like how 1, somebody said 1, 2 is in the natural numbers cross the natural numbers, but 1 is not in the power set of the natural numbers. Because the powers of the natural numbers is the set of all subsets of the natural numbers. So we could have the empty set, you could have 1, you could have 2, right? You could have the set 1, 2, you could have the set 1, 3. You know, like all the possible subsets of natural numbers you can make. But 1 and 2, 1's not here. The set that contains 1 is here. That's different than just the number 1. There are no numbers here. Right? The powers of the natural numbers is a set of subsets. There are no numbers. So being in one, so an element being the natural numbers cross the natural numbers, what that literally means, it only means one thing. Forget everything else. All it means is the first coordinates in the first set and the second coordinates in the second set. That is it. So that's why, for example, 15 and pi are in the natural numbers cross the irrational numbers. Because 15 is in the natural numbers, pi is in the irrational numbers. And it's also why, for example, 0.5 pi is not the naturals cross the irrationals, because 0.5 is not in the naturals. So literally the only thing it means for a set to be in the direct product is that the first coordinate comes from the first set, the second coordinate comes from the second set. That is it. So to show that xy is in A cross A, all you got to show is that the first coordinate x comes from the first set A, and the second coordinate y comes from the second set A. That is it. Does that make sense?
Yeah.
Yeah, that was a yes, right?
Yeah.
Good. Nothing more complicated than that. No power hits, none of that. Just that. So to show this, we need to show that. Now here's the kind of other side of that coin. To show this. So to show that xy is not an A cross B, based on what we just said, right? What we just said, if you're in the direct product, that means the first coordinates in the first set, the second coordinates in the second set. Based on what we just said, if xy is not an A cross B, what does that mean? What must fail?
That X is not in A and Y is not in B.
Close. If X is not in A and Y is not in B, then certainly you're not going to be in here. That's totally true. But do both of them have to not be in it? What if just one of them failed? What if just Y wasn't in B? If Y wasn't in B, is that enough to say that XY is not an A cross B? The answer is yes, absolutely. Because XY and A cross B, remember we said in order for XY to be an A cross B, the first coordinate has to be in the first set and the second coordinate has to be in the second set. But if we prove Y, the second coordinate's not in the second set, well then it doesn't matter what the first coordinate does, it just can't be in it. Right? Because it's an and situation here. We need the first coordinate to be in the first set and the second coordinate to be in the second set. So both of them need to be true for it to work. So both of them need to be true for it to work, then just one of them needs to be false for it not to work. And so Y not in B ruins everything, because that means XY is not an element of A cross B. So we really want an OR here. So to show this happens, we just need to show x not in A or x not in B. And same thing here. To show this, show x is not in A, or sorry, show x is not in B, or y is not in B. Or sorry, y is not in A. All right. So what we've done is if we can show x is in A and y is in A, then we know x, y is in A cross A. If we can show x is not in A or y is not in B, we can show x, y is not in A cross B. If we can show x not in B or y is not in A, we can show x, y is not in B cross A. All right. So if we can show x, y is not in A cross B and x, y is not in B cross A, we can show x, y is not in the union A cross B, union B cross A. It's not in one of them, then it can't be in either one of them. You just say, oh, sorry. If it's not in one of them, then it can't be in the union. Sorry. If it's not in both of them, then it can't be in either one of them. That's what this says. If it's not in both of them, it can't be in the union. But if we know x, y is in A cross A, and we know x, y is not in this union, well, then by definition, x, y is in the set that contains everything in A cross A minus all the stuff in the union. So if we can show this, this, and this, if we can show this, this, and this, we'll show what we want, because this is what we want to conclude right here. So now let's go back to the beginning of the maze. Here at the top, we worked at the beginning of the maze, and then we worked at the end of the maze, right? To try to see if we can meet in the middle. And so we left off saying that x is in A and x is not in B, y is in A, y is not in B. Well, heck, that means that x is in A and y is in A. Ooh. This is true. We also showed that y is not in B. Oh, heck, this is true. Because we just need to show that x is not in A or y is not in B. So we show y is not in B, we're good. And here we either need x not in B or y is not in A. Oh, we got x not in B. So x not in B shows this, y not in B shows this, and x in A and y in A show that. So then this goes up to show this shows this shows this. These two together show this and this together show this. So it should work. It should work. Now all you have to do is run this logic forwards. So just do this exact logic we were just saying. So I'll write it out. So what we were saying is that so first of all, note, or say then x is in A and y is in A means x, y is in A cross A by definition of direct product. Further, x, so that's the first one. We have it's in A cross A. Now we need to show it's not in the union. Further, x not in B implies that x, y not a B cross, sorry. Yeah, actually no, yeah, B cross A. X, y is not B cross A. Because in order to show this fails, we just need to show that x is not in B or x is not in A. If either one of those fails, then you can't have both x's in B and y's in A. Both the first coordinates in the first set, second coordinates in the second set. Next, y is not in B implies xy is not in A cross B. Hence, xy not in B cross A and xy not an A cross B, that implies xy is not in the union. If you're not in both of them, you're not in the union, which represents either one of them. We show why this is true. If you're not in both of them, you're not in the union. Thus, xy in A cross A and xy not in B cross A union A cross B, by definition, leads to xy in A cross A not B cross A union A cross B. Or you can do A cross B union B cross A. Remember, union's commutative, doesn't matter what order, or yeah, it doesn't matter the order. Therefore, since xy was arbitrary, we have that A over B cross A over B, A not B cross A not B is a subset of A cross A, not A cross B union B cross A. That's it. That's the first direction. Any questions? I think if you go through each and every step here, it makes sense. Just kind of the questions are like, why would you do that? Why would you do that? Like, why would you do that? Why would you do that? Why would you do that? And the answer is we work backwards. And so the backwards thing was we started with, okay, we want to get to here. We want to get x, y is an A cross A, not B cross A union A cross B. Then we thought, what do we need to prove that? Well, to prove that, we really need to know that x, y is an A cross A and x, y is not in B cross A union A cross B. Well, what do we need for that? Well, to prove x, y is not an A cross A, we need to know that x is an A and y is an A. To prove x, y is not in B cross A union A cross B, we need to know x, y is not in B cross A and x, y is not in A cross B. And to know that, we need to know that x is not in B and y is not in B. It also would have worked to know that x is not in A or y is not in A, or the other way around. It also would have worked to know that y is not in A or x is not in A. That would have also shown that x, y is not in here. But that's not how the cookie crumbled this time. This time it crumbled. The cookie crumbled in the way that we wanted, that we knew x was not in B. Yeah. Any questions? I hope this is making more sense. Now I'll do the other way, and I'll do it faster to show you. It doesn't take all that. I just kind of really explained every single step. So let's do the other way. So here we're trying to show that this set contains this set. So what that means is that every element of this must be in this. So let's go ahead and let x, y be any arbitrary / particular element of A cross B union B cross A. First step's deconstruction. Let's deconstruct what this means. Since xy is in A cross B union B cross A. Oh, sorry. Oh, no. Sorry. Wants to be an element of this. So it wants to be an element of A cross A, not A cross B union B cross A. Much different, much better. There we go. So then since xy is in A cross A, not A cross B union B cross A, by definition of set minus which is what this is. It's this set minus this set. XY is in A cross A, and XY is not in A cross B union B cross A. Thus, if XY is in A cross A, we know if XY is in A cross A, we know that X is in A and Y is in A. That must happen. There we go. Further, XY not in A cross B union B cross A. What does that mean? So we kind of talked about, this is kind of exactly what we talked about before. If you're not in the union, how do you relate to both? How do you relate to both of them?
Just like before.
Yeah. So what's that exactly? Like, could XY be in A cross B? Like, what's the relationships here?
X could be in A and Y.
I think we're skipping steps again, Afra. I'm just saying, like, let's just look at the big chunks. The big chunks being A cross B and B cross A. We're unioning these two things, right? So the question.
Okay, then my X should not be in A like AXB, and Y should not be in BXA, like the first part. If
I
we
think
look at the left side.
you're saying this.
Yeah.
Good. So you said that X is not an A cross B, which is true, but we're talking about XY here.
Okay.
Right? That's why I was getting a little confused. Yeah. Just making sure that's an important point. Yeah. So XY is not an A cross B, and is important. XY is not in B cross A. You can't be in both of them. Because if you were in either one of these, if XY was an A cross B, well, that's enough to be in the union. Because if you're in one, you're in the union. So it can't be any of them. So we have that. So we're almost deconstructed. So now we just got to know what this means. Next, XY not an A cross B. What's that mean? If you're not an A cross B, what's the mean about X and Y and A and B? What's the relationships there?
X not in A and Y not in B.
Close.
Actually, or like.
Or, yeah. Because you just need one of them to fail. You don't need both of them to fail. And just like how 1, 5, or I'll say
5.
1, 0.5 is not in the natural numbers cross the natural numbers. Because 0.5 is not the natural numbers. 1 is. So the first coordinate does work, but the second coordinate doesn't work. So you just need one of them to fail for you not to be in the direct product. Because direct product literally means first coordinate in the first set, second coordinate in the second set. First coordinate in the first set and second coordinate in the second set. So if that breaks down, then it's an OR. Yeah. Only one of them has to break down. Similarly, XY not in B cross A. We said that also has to be true. XY not in B cross A. What's that imply? The very similar thing, right? If xy is in B cross A, that means first coordinate in first set and second coordinate in second set. That means the x is in B and y is in A. But if we don't have that, what must happen?
Y not in B, or sorry, X not in B, or Y not in A.
Perfect. Yes, exactly, Afra. It's exactly right. Keep this in your head because you're nailing it right now. Yes, exactly. X not B. I just hurt my temples doing that. X not B or Y is not an A. So now we're deconstructing because we're totally just down to like X's and Y's and their elements. There's no direct products. There's no unions. We just have this. And so X, Y being in all this, if we deconstruct it, it means that X is an A and Y is an A. And it also means that X is not an A or Y is not an B. X is not an B or Y is not an A. Well, notice here, since X is an A, by elimination, what must happen with Y?
That X is in A and not in B.
Well, actually, it's going to be true, but we don't have that just yet. So all I'm saying here is that right here, we know X is an A.
Yeah.
Down here, we know we must have X not in A or Y not in B. So since one of these must be true, but we know X actually is an A, what do we know about this? Like if one of these must be true, but this one's false,
Then the other one is true.
the other one has to be true, right? So by elimination, Y must not be in B. Because we know X is not in A or Y is not in B, but we actually have X in A. So the only way for this statement to be true is if Y is not in B. Right? We're just using this fact put together with this fact. Like we said, there's X in A, that put together with X not in A or Y not in B, that implies Y not in B. And that's like an elimination argument. If you remember, gosh, elimination arguments way back when. And same thing here. Here we know, this is a fact. If X, Y starts in this set, we know we must have X not in B or Y not in A. But we also know Y is in A. So if Y is in A, this guy's false. So what do we know about this guy?
True.
It's got to be true. Since Y is in A, by elimination, X must not be in B. Good. So the point of this is what we've gotten down to, and put all this together, we've gotten down to thus X is in A by here, X is not in B by here, and we have Y, X is in, or sorry, we have Y is in A here, and Y is not in B by this line. So now let's kind of work backwards. So we want to get to this. Want to get to XY in A cross, nope, A not B cross A not B. Want to get to that. So if XY is, yeah, so in order to prove that XY is in this direct product, what do we really need to show?
Didn't we already show the part because we said that does X is in A but not but not in B. And also y is in A, not in B.
Yes, you're seeing it, Opera. You're seeing all the equations now. Perfect. Yeah. To show this, we need to show that the first coordinates in the first set and second coordinates in the second set. So we need to show that x is in A, not B, and y is in A, not B. Now, to show this, need to show that x is in A and x is not in B. To show this, we need to show that y is in A and y is not in B. We already have that. We know x is in A is x not in B. So we've shown this, that x is not in A not B. We've shown y is in A and y is not in B. So we've shown this. We've shown y is not in A, not B. Or sorry, y is in A, not B. And then you put these facts together, that x is in A, not B, and y is in A, not B. That's exactly what it means for x, y to be in A, not B, across A, not B, because the first coordinates in the first set, the second coordinates in the second set. So this leads us to, let's run this forwards now. Then x in A and x not in B implies x is in A over B by definition of set minus. Furthermore, add a furthermore, says even more fancy than further. Oh, you can see that, sorry. There we go. Furthermore, we're on the y's now. Y is in A and y is not in B implies that y is in A over B by definition of set minus. Therefore, misspelled therefore. Therefore, if you guys can even see individual letters these days, therefore, x is in A, not B, and y is in A, not B, right? In this line, we showed x must be in A, not B, because x is not in A and x not in B. This line, we show that y is in A, not B, since y is in A and y is not in B. So, xy is in A, not B, cross A, not B, by definition of direct product. So we started with an arbitrary element, xy, in A cross A, not A cross B, union B cross A. We can show that xy must also be in A over B cross A over B. Hence, since xy was arbitrary, we have that A over B cross A over B contains A cross A, not A cross B union B cross A. And we get that this set contains this set, because this set containing this set means everything in here will be in here. Everything in here is contained in here. This set like eclipses this set. And well, we showed that anything in here, x, y, must also be in here. So anything in here must be in here. This set contains this set. So we show both sides of the containment. And I'll say, finally, since both sets contain each other, they are equal. Whew. Any questions, Afra and Jai?
No.
I hope it's making more sense now. Now we've gone through everything. So the key really is deconstruct and reconstruct, right? We deconstructed down to here, I think. No, we deconstructed down to here. And then once we had that, once we knew how X and Y related to both these things, we started to reconstruct. And the key is when you reconstruct, kind of work backwards a little bit. You figure out what you need, like where you're trying to go, and you figure out what do I need to prove that? What do I need to prove that? What do you need to prove that? And then you just kind of work with that. The key is getting all our logic right. So the key is knowing that, oh, if you're not in the union, then you're not in both of them, right? But if you're not in the direct product, then that just means you're not in one of them. At least, it might be, at least you're not in one of them. You could not be in both of them, but at least you're not in one of them. And then, yeah, there's like, you can do the same things with intersections and all that. Just remember what your definitions are, and don't be afraid to do a little side work on the side and go, what's the opposite of a negation? Like if Z is not and C intersect D, what's that mean? Well, that means like Z can't be and C intersect D. And Z can intersect D, that means Z's in C and Z's in D. Because intersection means you're in both. Oh, but if I negate that, that means that Z can't be in C or Z can't be in D. Because if you're not in both of them, all that means is that you're not in one of them. But you could be, yeah, not in both of them just means that one of them fails. So one of them could be true and one of them fails. That's okay. But I'm saying that you could do that on your side, on the side by yourself for any of these negations. Or, like I said, you could always draw a Venn diagram. So the Venn diagram of that would be, if you look at, if this is C, and this is D. So you got Z here, and you got, or sorry, D here, C here. And now let's look at Z not and C intersect D. So if you look at everything not in the intersection, well, the intersection's here. So everything not in the intersection, it would include all that. It would include all this. It would include all this. Include all this. It's just everything not in this space right here. So if you're not in the intersection, you can be in C. Like an element here is not in the intersection, it's in C. Or you could be in D. You just can't be in both. Meaning you're either not in C or you're not in D. Or both. Anyway, the point is you have options. That's number 2. What time is it? Okay, I think it's time to go. Do we have any quick questions about Red Summit 12, anything on that, or anything else on the final before I leave and leave you to your devices?
So the test starts tonight, right?
Yes, the test is open tonight at midnight.
Okay, thanks.
And it's due 48 hours from then, Monday at 11:59.
All right, sounds good.
I forgot anything?
No, this was the one.
Good. Well, did we help here today?
Yeah, a lot.
Good to hear it. So I'm confident both you people. I think, I really do think, I'll tell you, that the final is doable. In the sense that there's really no question on the final, I think, substantially harder than a question that, oh, well, actually, most certainly I asked harder homework problems. So the final's easier than your homework. And I believe in you guys. I think you got it. So, I mean, study a little bit, you know, try hard, but as long as you do your business right, you should be fine. Well, anyway, people.
Thanks.
Yeah, it's probably the last time I see you guys. So, Afra.
Thank you so much for helping. It was really helpful.
You're welcome. Yeah, so Afra and Jayu, both pleasures to have in the class. And I wish you guys fantastic luck in the finals, fantastic winter breaks, and whatever you guys do, Guess where you guys are. Hope you guys do well.
Thank you so much.
Thanks.
All right. See you guys later.
See you.